So one that I mentioned before, we're going to be using Keras 2, and I have a link here for introduction to Keras 2. Keras 2, this was reported in March 2017, so it's brand new. And Keras 2 is basically evolution of Keras 1. And there are a lot of success stories right now of Keras 2. Keras 2 right now is branching into two forms. One is going to be, I think, part of TensorFlow, and another part which is going to be an API type which can work with any particular library. Okay, so there's a TensorFlow integration. You can read all these things offline, but they call it right now, there's improvements on Keras 2 that is viewed as an API that could work with a lot of different libraries. So it can work with TensorFlow, which is a Google library. It can work with Theano, which is an earlier library that's by the University of Montreal, and it's similar to TensorFlow in a way. And there's other libraries that this thing can support, and also they envisioning also the Keras JS, which is going to be JavaScript, that you can run this software or this API on your browser. Okay, so it seems that there are positive things that this one also will be available and independent from what these unique libraries evolution is. We're going to have a higher level, hopefully, library choice that as they maintain and change these other libraries, you can always have your code basically transferred and saved while the evolution of these different libraries takes place. So that's point. So how many people have installed basically Anaconda, or they have Anaconda on their PC? Or okay, so that's important. So you can go to that website, Anaconda 2, and you can download it on whatever platform you have if you want, or you could use HPCC as we have it, or you could use, obviously, the Google Cloud. All these are different options, and we'll be discussing those things, hopefully in Piazza, and it's going to be a group kind of discussion of how the improvements are. Okay. So before I delve into Keras, let's just go back to something that we've seen before, which is this Convnet JavaScript. And you could read from this website about it, okay, the description of it, developed by a former student at Stanford. And it has, for example, primarily these two data sets, the MNIST, which is hand recognition data set that's been selectively and groomed and prepared and split into a set of training, about 50,000 images of handwritten character recognition. Each one is roughly 28 by 28 pixels, or some other forms of 32 by 32. And obviously in these digits, you want to classify any image that you see of a 28 by 28 into one of the numerical values from 0 to 9. So you have 10 basically classes. So that's a classification problem. And the MNIST is, if you wish, a classical data set. That's the entry level. It's the basic data set that people could test their algorithm on. You have other data sets, as I mentioned before, the CFAR 10 and CFAR 100, which is for different images. And CFAR 10, that means you have 10 different classes. CFAR 100, you have 100 classes. And now you can think of what classification problems you have. And here you have an interactive classification toy problem for 2D data set. So I'm going to begin with this one here. Okay? So when you click on only these things, actually the browser will be executing the code, and you see the results in graphical thing. This is a nice, intuitive way of feeling more comfortable with what these things are. So if I look at the model in this case, and by the way, I just walked into I don't know JavaScript myself. I know Python, but I don't know JavaScript. And you can learn how to basically change these different equations to have a different performance. So for example, I've learned that I think the commenting this thing here, so you have two outputs here, I can comment one of those things. So let me comment maybe this one. I comment, I believe it's slash, and then I change basically. So right now, what I have the layer definitions, then this layer definition push defines the input layer. You can read through it and you can read it and pick it up quickly. And now I don't have this layer, so I have this one layer. So I have an input layer of two-dimensional input, and then I have an output layer of two-dimension activation. And this activation tells you what nonlinearities you have. And in both of these things, they selected nonlinearity to be hyperbolic tangent. You could replace this one by sigmoidal nonlinearity or other type of nonlinearities and see the performance. But what I want here is that you have, in this case, you have the input space, let's say x1 or x2, whatever the input space is, and you have data in different colors. You have two classes. And this is the performance that eventually with this single layer, now I have a single layer which has really partitioned this space. Every output is going to have a line and partition the space at the end of the training in this case. So if I change the data into another set of data, say simple data, and as you can see, the lines here between the two colored regions, each line is representing an output, or at least defined by the output, one output. Because you have two outputs, you have two lines, and then the lines will move and they settle when you have the two classes partitioned. Okay? So what if I come here and I say, I don't want two outputs, let me just have a single output. So here I'm going to change this one to 1 and see what happens. I change the network. And now, single output, I have basically one output, one line, because I have one output. The single layer network represented a line in this case, the input space two-dimension, and I have a single output. The equations of the network represents a line. And this boundary here separates, let's say, the +1 and -1 classes. And you can see with the one thing, I have one green here what belongs to one region. So this classification, the best it could do is classify it this way. So I have this value is misclassified. So that's one thing that I urge you to go and check it out. And of course, you could go to the MNest if I get connected. So here's the MNest demo. And you could see it with this JavaScript, this program, run things in real time. You could see it. And this, you have the loss function. You see how it decays at every update. You could see all these parameters, how much time it takes for a sample to pass through. And back propagating time, network, and the classification loss, which is a cost function or loss function. That is used to measure the performance. You see it should be decreasing, and you see it visually here is decreasing. Sometimes it goes up temporarily. Validation accuracy, you have training accuracy, which is the data that you train to see the accuracy. This is 1 becomes 100%, and this is really 93% accuracy under the training. However, the validation data that you use to test the performance is less. The validation data obviously is not seen in the training. And in this platform, you could change the learning rate, which is the eta. Momentum you can change the momentum, the batch size, which is the number of sample you use to average to get the change. The weight decay, that's another term that we didn't talk about. You have another term for weight decay, which is related to the momentum in a way. And you can easily change the network by looking at what we have. This is obviously, this is an implementation of a convolutional neural network. So, it's similar to a feed-forward neural network, but it has a different structure. And it shows you all these details, okay? This enables you to gain maybe more insights if you never had any experience with that. The third thing that I want to go is that we can go to Keras itself, and Keras has a set of examples that are available with Keras. And in the set of it has a lot of initial examples you could use. And we are looking at MNIST multi-layer perceptron, or multi-layer neural network. So we can click on that example. And I can download or copy this example in my Python and Keras, and I can execute it. So what I do, I can go to my command line and log in, and what I have here, let me see if so I can have, once I install Anaconda too, Anaconda is going to install all these different programs. Then I can have the list, Conda list, which is part of the Anaconda, just list all the codes that I have in my package, okay? Everything that has PY27 to it is like, my Python is 2.7 that I installed by choice, which in the past when I installed this one was the one that's safest to use with all the libraries. Of course, things evolve all the time, and you look at what the latest information of the libraries. The only thing you need to add to Anaconda are two things. For example, either TensorFlow or Theano. So what I've installed here is Theano. So I'm looking for, under the list here of all the programs, here's Theano. And the way I enlist Theano is actually use something called pip. How many people know what pip is in terms of installation? Okay. So pip is, Conda basically installs all the programs that have interdependency in a nice package for you. It's a nice environment where it guarantees that every package is going to work with every package. So Python and all the other stuff in the list, they all work nicely. Work nicely meaning you have the right version. So every developer updates their code every time they have new versions. So we want to make sure the dependency among these versions is smooth, and that's why you go to an environment such as Anaconda 2, guarantees all these things well. I'm not sure if Anaconda 2 now has Theano in it or not. Last time I installed it didn't have, so that means I have to go and install Theano or TensorFlow. And I've used pip, which is another program for installing new packages. And the other thing I installed here is Keras. And I'm not sure, again, if Anaconda 2 has Keras in it or not. Last time I installed it didn't have it, so I used pip to install it. So if I look at the list, I have Theano here, I installed it. And I used pip to install it, which is here. And I've used actually in my installation here the latest. Typically they tell you not to install the latest. We can go to the installation page for under Keras. We can find the installation. It tells you how to install Theano and recommends that you install version 0.9, okay? Which is, I believe nowadays it's part of Anaconda, but it may or may not be. Well, last time I installed it, it didn't have it. But I chose here to install the later than 0.9. I installed 10, which is called the development version for my own purposes. And so that's one. And the other one is Keras. So if I look at my list here, K, I'm going for K. So here, K, Keras. And if we look at Keras, again, I use pip to install it. And I have this version of Keras, which is Keras 2, version 2.04. So I installed those things in order for me to use Keras. So those things, either you need Theano as a back end or TensorFlow as a back end. So if I go to introducing Keras, I'm not sure. So I can go back and you could, so here's the list, and then somewhere, yeah, so here's Keras. You can look up examples, you can look at all the examples, but if you say, it should tell you something about installation. So somewhere here, I think I saw installation. I'm not sure I see it now. But this, for the sake of people who are still behind in doing the installation. So here is installation. It tells you if you want to install TensorFlow with Keras or Theano. So if I go to the specific one I installed, which is Theano, it tells you what platform you have. I have Windows on this machine. And then for Windows, it walks you through all the do's and don'ts for the installation. And it gives you the exact commands that we talked about for installing it. So you can use, I think you could use Conda install or pip. These are the two options. So, so with Conda, you can install actually Theano with Conda as well, and it's going to get the right version for you. So I'm walking with everybody. I want to make sure everybody's on board. Hopefully the Piazza thing is going to help us out in communicating. And I want those who are familiar to help out in answering any questions. And you gotta get on with it and start basically getting this thing code working. So there is a choice in when you want to run your codes. So the choice, let's see if I have it here. So you can either use Spider, which is a program, interactive program that you can Python. How many people are familiar with Spider? Please raise your arm, that would help. Which comes directly when you install Anaconda, you have it there, and you could go to your program and just type Spider and we'll spit it out. And it's a graphical interface for running codes. Another option is Jupyter, okay, which is a different interface for running codes. How many people are familiar with Jupyter? Okay, I have 4 people only, okay? So I'm going to rely on you people to kind of answer those questions when you see them in Piazza, okay? So again, Jupyter is part of Anaconda. Once you install Anaconda, you have it's a huge interface package that's ready to run. And the way to run Jupyter, I'm running it here obviously on my Windows. You could also have Mac or Linux system, and you just type in Jupyter, as I have it here, okay? And you type notebook. The beauty about this is that when you type it, it basically opens, here's the word basically again. So it opens something in your browser. Wherever you're at in your directory, it basically opens this thing, and you could come in, and in this case I've selected so anything that's IPYNB, which is Jupyter Notebook, it's a program. So if you look at this one here, which is the same example MLP PY example that I showed you earlier, which you copy from Keras. So this is just the raw example. I just copied it and I wrote here the word Keras example just to remind myself this is from Keras. This rest of it is just copied it and pasted into this location. So once you have the home, you can click on any of these IP and and run one of those. It opens Jupyter for you. And the way to run Jupyter is just have full code or part of a code, anything you want to run in a cell. So this is one cell, okay, and you could run your program in pieces or you run it all at once. So this is the whole example. I ran it earlier and it gives me the structure of the network because it's, I'll walk through the example here because there's a importance here that we could see, and tells me the structure of the network. I have a network with so I have a network with a dense. It has a dropout. Dropout is another layer that just drops out some of the outputs of that particular layer. Another dense layer which is fully connected. Another dropout, another dense layer. And here you have 10 outputs. This one here, this dense layer has 500 outputs. The input will be the dimension of the input space. Tells you all the parameters. So this is a summary. And then that training, this one uses 60,000 samples of images, 28 by 28 each, to train on, 60,000. This data set has 50,000 for training, 10,000 for validation, another 10,000 for testing. Sometimes you merge the training with the validation, use it in the training, and that's why you have 60,000 in this case, and use only 10,000 for testing. So let me back up here and just go to Keras, and this Keras.io tells you about Keras. You can actually use TensorFlow, CNTK, which is another library created by Microsoft, and then Theano. All these three libraries are evolving and changing over time, and this Keras can actually work all of them. Also, because the developer of this package, Keras, happened to be working at Google, Keras has another version that's implicitly within TensorFlow. You can have an option of Keras. They can tell you all these things. So what I want here is just you could read these pages. You can look at how to create it, which is very simple. You create what's called, in this case, sequential model, which is you just call the library, which is from keras.models, import the sequential model, and then you define your model. You say model equals sequential. You can call it anything model, and then that will becomes your model, and then you're going to stack one layer. Remember that feed forward or any layers, it's in layering, stacking, sequential blocks. So you can use the model.add, which adds a dense layer, which is fully connected. You can define this dense layer output is activation function. In this case, they define it to be the RELU, for example. In this dense layer, the first layer you supply, you have to define what the input dimension is. Then you have so this is one layer. Then you have another dense layer. And you say how many units for this dense layer? 10. So from 64 feeds into 10. And then the last one, for this 10, you have a soft max, which is similar to, we'll define it later on, but similar to the sigmoidal function. It's a soft max is often used to provide outputs that are between 0 and 1, which mimic probability. So you can say, okay, my output is probability or strength or confidence. So when you say output 1 is equal to 0.8, it's like output 1 is with confidence 0.8 or probability 0.8. So that sometimes we use the softmax. So you define your layering. Then the next thing is to compile it. So you define what particular cost function you're going to use. In this case, we use categorical cross entropy, which is a cost function. We use the SGD, which is stochastic gradient descent. We use metric, which is accuracy. You want the accuracy of classification. Okay. So this is, you can also have the compiling where you can specifically specify the SGD. So you don't have just the generic default SGD, but you actually can spell it out by saying my optimizer is going to be SGD here, and you want to have a learning rate of 0.01, you want to have momentum of 0.9, you want to have Nestro, which is basically the learning algorithm type, is chosen. The fit function is that when you do the training. So once you define your network and you define the compilation, everything is ready. Then you just basically fitting is do the training. And in the training, you also provide the training data, which is the input and the target, which is referred to as Y train. You decide how many epochs you want to train, which means epochs passing through the whole set of training data. In this case, if you have 60,000, you have to pass through all the 60,000. And the batch size is that before you update the weights, how many samples you're going to use to update the weights, which is the batch size. In this case, 32. And there are other techniques where you can define it, train it on a batch. You can actually do the training. So this first one, the fit, applies to all the available data, which is the full training data, the epoch. This other alternate method, suppose you want to change things between one batch to the other one. For example, the ADA or something else. You may want to define it over one batch and then you iterate. You have a for loop to iterate over these many batches. And then the evaluation is you have the evaluation data, which is not used for the training. You want to see the performance of this particular metric. So you can walk through and do this thing. If you do that, then we go to this particular sample program. And we go on the top. And here you have print function from future import. You're importing from this library future, the printing function to be able to print. Then here, he's importing Keras. So all the functionality in the library Keras becomes available to you in this case. That's a choice. Sometimes you don't need to import everything in Keras. Sometimes you say import Keras as K or something. Okay? And this one here, from this particular subset of the Keras library, the data set, you're going to import one data set, which is available in the library, thankfully, MNIST data set. And then the models, you're going to have the sequential. There are a lot of different models. We're selecting the sequential. Then the layers, you want a dense layer, which is fully connected. You got another one, which is dropout, which means from this fully connected, you can select randomly which operator you're going to set to 0. That's where a dropout is. You can insert the dropout block anywhere you want. Keras optimizers, in this case, they selected this particular optimizer. You can look up at Keras and find what optimizers are available to you. There's another optimizer that sometimes works very good in practice called Atom, or Atoms, and other versions of Atoms, okay, which has different kind of flavors. Sometimes a good practice in running your program, and this is obviously this class is not about programming in any way. I'm just going to take time here just in case you need to catch up and allow you to have any questions and those who are bored, maybe I have to apologize. Those who are not, please bring yourself up and know what needs to be done. Okay. Sometimes it's good practice to have some random seed, and this is I don't have NPy. I didn't basically import NPy, but you could, for example, have random from many sources, random function, but you could have, typically my practice to import also NumPy as NP, and then you have np.rand seed, and you select some number. And the advantage there is that when you run your program, you want to have reproducibility. If you want to run it again, you're going to get the same result. So for example, in this case, because I don't have random seed, they claim in the example this is the exact testing performance after 20 epochs. I ran it 20 epochs. I didn't get the exact number. If I had the same seed for selecting the initial conditions of the weights and the parameters, I will reproduce the exact same thing. So sometimes it's a good practice when you claim that you achieve this accuracy, make sure you have that seed, because then you can reproduce it. So here you list the so-called parameters. So the batch size, you can specify that. At some point, you're going to use that function, so you label it batch size. 128 they use here, which is many samples. Remember, you have 60,000 data, and they go 128. Typically, they go from 16, 32, 64, 128, 512, just to select some group, depending on the size of the data. Number of classes in our problem here, 10, obviously. We want to classify the digits 0 to 9. Epochs, you can select it 20. And the data shuffled and split between training and test data. So there's this MNIST load data, which is available in Keras, that just has the MNIST data and splits it in the usual way, training and testing, and the training will be 60,000, the testing will be, data will be 10,000. Reshape, so I told you the data, the 60,000 samples, stored as 28 by 28 array. So you need to reshape it, convert to a vector, because you're going to apply it to a multi-layer neural network. Okay? So 28 by 28, you multiply it, that's 784. So you reshape the data, the training and the test data at the input, into vectors of dimension 784. And you have number of rows 60,000, and this is, for every row you have 784, which represents one image. Okay? So you have it in the accuracy here, you have a float, 32. You scale, these images are in gray level. So they're image between 0 to 225. So you divide by 225. So then basically every value of pixel becomes between 0 and 1. Right? You could print. That tells you, this shape tells you how many in the rows, because you're selecting 0, which is the rows in both cases. You convert the class of vectors to binary class matrices. So what does that mean? The training data, the y, which is the desired value, is given to us as a number 0 to 9. Okay? So y train is really a vector. Each component is between 0 and 9 integers. So you want to convert each one of those integers into a vector, which is called one-hot element vector, which really gives you a vector of dimension 10, and you have 1 in the location of that number. So the number, which is whatever the number is from 0 to 9, is going to be actually the position of that vector to place a 1 there. So this is converting the vector of integers into an array where every row is going to be a row of all zeros except one number positioned in the corresponding value of that integer. Okay? So this is just a way of converting the reference value into a vector. Because you have 10 categories, you need another vector. One of these values is going to be high. High probability is going to be that particular number from 0 to 9. So we encoded the value in the position of the vector. So here's my sequential, or the sequential of this example. You create the model sequential, you add dense layer. So the input is, we said 784. Here's the input shape, which is a column vector. The first output here, which is a dense, is going to be 512 units, hidden units. And then you insert here a dropout, which means 20% of those outputs are going to be set to 0 randomly. Okay. From 512, 20% of those randomly each time basically will be set to 0. And then this one is going to go into another layer with outputs 512, another dropout, and finally you have the output 10, which is the classes. And the output is sigmoidal type. It's called softmax, which emulates probability. And at some, we can look up the softmax, but basically it's going to be e to the output over the sum of the exponential of all the outputs, which is going to render all the outputs equals, each output is going to be between 0 and 1, and the sum of these outputs is going to be equal to 1. And model.summary just summarize for you what network you have, which you could see the output of model.summary is going to print out this thing here, which just tells you what the layers. So you have the layer, dense layer, dropout, dense layer, dropout, and then dense layer. It tells you the shape or the output of each one of those layers. And then also tells you the total number of parameters that you need to update. So look at the number of parameters here. The number of parameters you need to train in this training process. And then we don't have any non-parameters, nothing to be trained. So you run this, and you're going to have your training on 60,000 samples, validation 10,000 samples. It's going to print for you every epoch, this epoch 1, which is passing through all the data, and incrementally going to show you this. We're going to see this one in action in a second. It takes 8 seconds per epoch on my computer. They say in the comment that takes 2 seconds on a GPU. It takes 2 seconds per epoch on a Kepler 520 GPU, which is NVIDIA type of GPU if you have one. So on my computer here, which has an i7 processor, it takes 8 seconds. Tells you the loss function, which on the training, the accuracy on the training, the validation loss on the data that you do the validation, and then the accuracy on the validation. So it starts at pretty good. So in fact, in this case, you have the training is 92%. The validation happens to be, in this case, you got lucky, you have it higher on the validation. However, as you move forward, you're going to see that the training catches on, and then the training should at least exceeds it at some point. So here you have 99% on the training, but the validation did not go beyond, in this case, 98%. And you continue from 98% in a fraction all the way to the end of the 20 epochs. And my number here is 98.33, which is different than his number, which is 98.4. Because we have different initialization, random initial conditions. If I use the same seed, I would get the same result every time. And it's a good practice to do that. So I have a few minutes, 5 minutes, and in 5 minutes I'll tell you, once you have this program, whatever code, you just go to the last sentence here, and if you don't want to create another cell, if you push Control and then Enter, it does not create a new cell for you, which is the next cell. If you just hit Enter, it's going to create another cell. I'm going to show you that. So my practice is to push Control and then Enter at this point, and it's going to run it from scratch. And notice the first time you run it, it's going to tell you what back end you ran. So I had like Theano at the back end. This time it didn't show it because it already told me that. So as you can see here, it's running, and that's how the speed is. So in this case, I have 12 seconds to execute one epoch. Before, where I ran it was 8. Apparently, I have a lot of different things right now, so that slows it down. The process taken that much time for some reason, and then 14 seconds. And I should actually, my intention was to run it only for 2 epochs, but I pushed the button. So it's going to be running for every epoch, and you can see the performance. Again, this is the training data. The validation data is not part of the training. It just, you evaluate on it, and it's 96%, 97%, 90, this one from 92% to 96, the second epoch. Third epoch is already 97%, catches on. And then now it's 98, the fourth epoch, 98%. And so the training could go higher, but what you're looking at eventually is the validation of the testing, which is the data that the training is not using. And it reaches already 98%, and goes down to 97 sometimes, and what have you. So we have 3 minutes. Any questions? Yes?
Why couldn't you just have one output with the method and then just use one classifier? Or one, 0 to 9?
Yeah, you could have one output which tells you a number from 1 to 10, right? So it's easier to have this categories where you have vector, this strategy of selecting references to be the so-called one-hot element, where you have 1 somewhere in the position and the rest of 0, makes it easy to do that classification. You're challenging the network if you want to do it the other option, and it becomes, you're adding more difficulties. So typically, you do it basically by this splitting and having this different categories. Any other questions? Any comments? We have 2 minutes here.
Are you still running the Convnetjs example? Is that slowing it down?
It's probably, it's still doing. Maybe that's what slows it down. Yeah, it's still running. Yep, absolutely. So it's sharing, and so that's what slows it down. So let me see if I turn this guy off totally. See happens. I don't know if that works here. Should we see the epochs change? Well, here it went down. So maybe. So let's see what happens at the end. So you see it. So the reason it incrementally goes through batches, 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 and updates until it goes through the whole data set and repeats. Now, one comment, we went through the gradient descent and the derivation, what have you. These libraries, the TensorFlow, Theano, all of them use symbolic programming to execute the derivatives for you. So you don't have to do the derivatives. So you just, as you can see here in Keras, we just define the network, and we say we're going to use this, the cost function that we're using, and the software goes inside and calculates symbolically the derivatives. This is good if all you want to use the existing techniques. If you're a researcher like us who like to invent new things, sometimes you have to go down under the hood to the nitty-gritty and modify things. Sometimes you're not happy with this particular gradient. You want to modify the gradient descent. So there's positive thing in executing things quickly, and you don't have to worry about the computation of the gradient because the software is doing it for you. But you could at some point meet a challenging scenario where that particular numerical technique or symbolic technique would not work, or you want to alter the update law. So that's just a comment in general. And with that, I think we're reaching the end. And thank you all.